Hi. Uh, hey, I guess first, thanks for having me. This is pretty rad. This is a good reason to come out to New York from San Francisco. I actually love it here this time of year. This is fantastic for me. So, thank you. So this talk kind of came out of a bunch of research that I was doing last year, trying to find a better way to do load balancing. And it might seem like an odd topic for this group in a lot of ways, right? Like load balancing, a lot of times when we talk about it, is not really about performance. It's more about I have a group of computers and I want the computers to do a thing together. And so I use a load balancer to make them do the thing together. So a lot of this talk talks about like how load balancing isn't quite as, in a lot of ways, like innocuous as you might think when you're talking about performance. And it can actually lead to some really interesting performance problems. So I realized that most of us are using random or round robin for doing our load balancing these days. And that struck me as kind of odd, right? Like, we're a bunch of engineers, we're a bunch of operations people, low-level engineers, high-level engineers, all kinds of engineers, and the best we can do is random or round robin? Really? Seems odd. So I guess some spoilers for this talk. I don't really have anything to sell you right now. I work at Fastly. I'm the CTO at Fastly, but this talk isn't really about Fastly. This is about some research that I was working on last year for the most part. But you should use Fastly because it's awesome and we do what we do really, really well. Thanks. Also, I don't have a solution to this problem. I'm not joking about the title. It really is impossible to do this correctly. But ultimately, I want to try to show, try to be able to maybe explain some of the performance problems you might see, like one-off weird things that you might see as you're performance testing sites. Maybe you'll have an explanation for those now. So, right. I'm Tyler, CTO of Fastly. You can argue with me on the internet right there. It's pretty cool. Most of the things I work on at Fastly at this point are actually research-based. So it's projects that may fail, as in fact the load balancing project did. So first of all, what is load balancing? You can have a diagram here, but I couldn't really think of a good diagram to put here. So we're going to do an allegory instead. So, this is actually a story that someone who we work with, this guy named Hooman Beheshti, who was an early kind of load balancing pioneer back in the mid-90s. It's a story that he told at a conference in Canada in 1998. So he's the former CTO of Radware and Strangeloop previously, and now he sits across from me at work. Haha. So the story goes like this. We've all probably been in this situation before. You've been at some sort of sporting event, some sort of theater event, something like that, right? And there comes this moment in all of these different types of events where everything stops, and everybody gets up, and it's halftime, right? Everybody wants to go get a drink. They want to go get a beer, they want to go get some wine, they want to go get something, right? But there's only so many places that you can get those at, right? If you walk out into the hallways of a stadium, it's not just a single beer person for every individual person in the stadium, right? There's a few different places where you can go. There are some that are closer, there are some that are further away, there are some that have more people working at them, there are some that have less, there are some that have the particular drink you're looking for, there are some that don't. Right? And so this is actually a great way to describe load balancing, right? Because it could be that the most efficient way for you to get that drink that you want is actually to walk all the way to the other side of the stadium where there is no one waiting in that line, right? Instead of waiting in a long line that's right close to you, right? And so it has this interesting problem where you need to be able to predict whether or not the place that you're going to go is the fastest place for you to go. So that's essentially what we're trying to do with load balancing, and we get it wrong. So why do we do load balancing? As far as I'm concerned, there's actually three separate reasons why we do this. One is abstraction, right? It's kind of what I was describing at the beginning, where we have all these servers, and we want to be able to treat them all as one single entity, essentially. We want to have a single entry point to a group of tens or hundreds or thousands of servers. So it's about simplification. There's also failure, right? We want to have some sort of transparent failover type situation going on. We want to be able to recover seamlessly. We want to be able to fail over seamlessly. Again, it's about simplification of a problem. And then, in my opinion, the distant third is actually balancing load. But that's the part that I want to talk about today. So the problem of balancing load efficiently across a bunch of different servers. All right. So, random. Right? This is what most of us use. This is what Fastly uses today. This is what like basically every company I've ever worked at has used for their load balancing. It's either random or round robin. So why do people do this when it seems like kind of a silly idea? Like it's just random, right? Like what's good about it? Well, essentially what it comes down to is there's not much that can go wrong with random, at least on like a wide, like a large scale way. It's simple. There are very, very few edge cases in random. It's very easy to fail over, and it works exactly identically when you have multiple load balancers, when you have distributed load balancers. Right? You know, distributed random is in fact just random. You just do it randomly. You continue to do it randomly, and now it's distributed random. Good job. So this is kind of as opposed to some of the like more complex load balancing designs. So like least cons, for instance, which is often referred to in like the operations communities as like the finger of death. Because what happens is this, you know, you have your least cons load balancer sitting there, and it sees that one node doesn't have any traffic, and so then it suddenly directs all of the traffic over to that node, and that node is dead. And then, oh, okay, we'll spread it over here, and then this one, oh, now that one's dead too. And so it ends up being this really complex scenario where like, especially when you're getting into distributed situations, where it ends up being a problem. And that's why people end up using random a lot of the times, because it's simple. There are no edge cases to it. What's bad about random? A lot of it comes down to latency. And hopefully I will prove that to you throughout the rest of this talk. So, who here has heard of the balls into bins problem? That is awesome. I am so glad that none of you have. I'm happy to introduce you to a new statistical concept. Fantastic. So the problem goes as follows. If you throw m balls into n bins, what is the maximum load in any single one of the bins? Right? And so there's an obvious answer here. The answer could be m, right? You know, if you happen to randomly throw all m balls into one bin, then it would be m, right? But like, the question is really about like with high probability. Like it's incredibly, incredibly unlikely that if you have a large number of balls and you choose randomly that you're going to throw all of them into one single bin, right? So with high probability, what is the answer to this question? Well, it turns out that this is like a kind of classic problem in statistics. And there is a number of different papers that attempt to address this problem. This is my personal favorite because it's completely incomprehensible to me. But it's like, it seems to have like the most complete answer to it. So let's try to figure this out. So here, you know, okay, we start to have our first answer for, okay. So this is the answer if m is equal to n. So it'll be on the order of log n over log n. Okay. So if m is greater than or equal to the log of n, then that's the answer. It's order of m over n. Okay. But more generally, if you want to try to answer the question completely, that's your answer. I have no idea what a polylog is. I'm an engineer, not a mathematician. I have no idea. The answer essentially is that it's real complicated. And so when I was trying to, like, when I was looking into this problem and seeing how it relates to load balancing, I did the same thing that probably all of us in the room would do. You know, I wrote a script. So we're kind of going to build on the script a little bit as the talk goes on. But so just as an example here, so like here we have n, where n is our number of servers. Let's say we have 8 of them. We have m, which is 1,000, which is the number of requests that we're like processing. So we basically just make our number of bins. We iterate through the number of requests and choose randomly for each one and increment each of the bins, right? And so probably expecting that it's basically going to come out pretty even, right? You know, it's a uniform distribution. It's random. It should be fine, right? Not really, though. And so this is a pretty typical run of this thing. So you have like 100 being the lowest and 148 being the highest for the number of requests that each of those, or the number of balls that each of those bins got for this particular run, right? But this still isn't quite right, you know, because this isn't really modeling load balancing correctly. Like, not every individual request has the same weight, right? So if we want to model load balancing with a simulation like this, we need to do better. Okay, so let's continue to like iterate on this. Okay, so here, rather than just incrementing each of the buckets by 1 each time, now we're going to actually choose the bucket randomly, and then we pull from a uniform distribution. The mean is still going to be 1, but we're going to choose between 0 and 2 for each of our individual requests. So now we're going to have like this like variation in the weight of each of the individual requests, right? So, okay, so how does that change things? Oh, okay, it doesn't actually. It's about the same. All right. But this still isn't right. You know, every individual request, it's not really a uniform distribution that we're looking at when we're talking about individual requests going through a web server. So really the problem that we need to answer in this case is, how do you model request latency? So there's this nifty thing called log normal distribution. And it turns out that just about every application's request latency can be modeled with a log normal distribution, which looks roughly like that. I had read this before, but I wanted to test it, and so I pulled the request latencies from like a bunch of different, individual like services on the CDNs, and yeah, and it turns out that like it's all different curves, but this is like, they can all be kind of modeled roughly against the same distribution, which is really interesting to me. But so let's look at this distribution. So like with this one in particular, our mean is 1. So with this distribution, we have a mean of 1. If you choose randomly a bunch of times, you can divide them all by that number, you're going to get 1. But the 50th percentile is 0.6. 75th comes in at 1.2. 75th is starting to get exciting now. We're going up pretty rapidly. There you go. You get us like the 99.9 percentile, and you're talking about like for a distribution that has a mean of 1 second, you're getting up to like 14 seconds. 1 in 1,000 requests is going to take roughly 14 seconds if your mean is 1, at least with this individual like specific curve, right? And so I did in fact like pull some data for this, and here are some examples of this. So these are like individual services. I'm certainly not going to tell you who they are, so don't ask. So these are like 4 different sites that are going through our CDN. And so we have one that's an example of a user-generated content site, and you see that exact same curve, modified with like different parameters, right? With minor tweaks to the parameters. You see a social site here that has a like slightly more like gentle curve. You have a photo site. Of course, they're serving larger objects, so that curve is going to be like a little bit more gradual like that. And then you have ad serving sites down there in the like the left corner where it's very flat until it's not. Then it spikes up. But everything ends up following a very similar curve. So okay, let's plug that in and see what happens. So this is that same example, except now I'm using the log normal distribution to pull the request latencies from. We also added in a baseline because no request actually takes 0 seconds. It's great. Okay, so what does this look like? It is way, way, way more skewed than even just the normal falls into bins problem. And so this is why perfection is impossible. I'll explain. What this comes down to is that it requires an advanced knowledge. It requires knowledge ahead of time that you cannot possibly have. You cannot predict how long an individual request is going to take because of various things that happen across the network. There's packet loss, there is like slowdowns, there's garbage collection, there's all sorts of things that happen when you're actually like doing a single request, such that it may fall anywhere along that curve, and you can't actually predict this. And if you can't predict this, you can't do load balancing perfectly. And I will continue to explain why that is a problem. So let's say this is our cluster of servers. Right? Look at those happy computers. They're so optimistic. They don't know that a load balancer is about to ruin their life. We have our very confused and lonely request here who's just looking for a home, right? Okay. So let's say it's going through a load balancer here. And each of those servers has a queue, right? We know how many, let's say, requests are going through each of them at this moment. And so let's say it looks something like this. So the top one, it's 1 large request. The bottom one, we have 4 tiny requests. In the middle, we have like 2 normal-sized requests, right? And so obviously, the ideal scenario here is that this request should go through the load balancer. The load balancer should realize that the bottom one is the least loaded and choose that, right? Right. But the problem comes down to that we can't actually know how long the individual requests in those queues are going to take, which means that the only knowledge that we can have is a number of requests that are outstanding. And so we're going to choose the top one, even though that was the worst choice for us to make in this case. And because of that log normal distribution that all of these are following, this is a very likely scenario. And so our happy computer goes to being a sad computer. So what effect does this end up actually having, right? So this is from a simulation that I've been running, and I'm going to show more and more simulation numbers throughout the rest of this talk. So we had like a theoretical system that I was simulating doing this research, and the distribution, the green line here, that it was supposed to be simulating looks like that, the green line, right? But as soon as you start running it through a random load balancer at about 70% of the capacity of the system, it starts to look more like that blue line. And so it ends up making that request latency, that request distribution, worse and worse and worse over time. But why does that end up mattering? Well, who here is familiar with Gil Tene? Yes, again, introducing really cool stuff. Okay, so Gil Tene has been writing about latency for a long, long time and has written some like fantastic articles about why long-tail latency matters a lot, especially for user performance, for end user performance. So the way this ends up going is something like this. So we have the probability that a single resource request is avoiding the 99th percentile is 99%, right? Obvious, right? So the probability of all n requests in a single page avoiding the 99th percentile is 99% to the nth power. So as soon as you have 69 requests on a website, more than half of your users are going to be hitting the 99th percentile of latency. So 69 seemed like, I'm like, but like who actually has 69 requests on their like homepage? That seems silly. Like who would do that? You know, you have your CSS, you have your HTML, that's silly. So Amazon currently has over 100 requests on their homepage when you first land there. One of the conference sites that I gave this talk at previously had 190. Facebook has well over 200, and CNN had 700 before onload was triggered, which means that at least in that last case, they weren't just hitting the 99th percentile of latency, they were hitting the 99.9th percentile of latency on most page loads. So this long tail latency really, truly does matter. Okay, cool. So one of the interesting parts of this that I like ran up against as I was starting to test these systems is that you could kind of solve this problem if you ran your system, if you ran your load balancer with way, way, way too much capacity. So okay, so let's say that we have 10 servers and each of them can handle 10 requests per second, right? Now let's say that we are overall doing 100 requests per second. You know, great, okay, cool. That's 100% of the theoretical load, right? But let's say we have 20 servers then. So we have twice as much capacity as we need. So if you look over on the left side here at like the 50% load, which is what we're talking about, that's what the like distribution ends up looking like if you're running through a random load balancer. So the P99.9 over there is only just below 1. But as soon as the load on the system starts to increase, those long tail latencies get worse and worse and worse. This is an effect of randomness on the system, because as those requests are piling up, there becomes this high likelihood that at some point, you're going to end up sitting behind a very long number of requests before you actually get your response. So what do we do about it? There's got to be some way to do it better than this, right? So there's an algorithm called join shortest queue, which is basically what I was showing there with the like happy computer simulation, diagram, whatever. It's still not perfect, but it does do a hell of a lot better than random. So like, what does JSQ look like? Well, it ends up looking kind of like that. So in this case, that green line is now JSQ, which is much more close to what our actual distribution looked like. Great. Another way to look at this is from the perspective of the application servers. So let's say you have a bunch of application servers that you're load balancing between. And so what this is showing is actually the origin loads on each of those servers doing random load balancing. So each of those lines is essentially showing like the number of outstanding requests at each of the application servers over time. The point here is that this is a high amount of variance, right? So like the difference between some of them and the others is like wide. It's a large number. And this is using join shortest queue. So you see that it's still not perfect. It's still not like actually like all the same number the entire way through, but it's about as good as we can do. It's much lower variance than random. So if you just have one load balancer, if you're running through one single load balancer, join shortest queue is pretty good. It's probably about as good as we can do. And so again, this is kind of going back to that same like as load increases on the system, like with join shortest queue, that's the wrong label there, that's fine. But with join shortest queue, you get up to 90% load and it's still not that bad. It hasn't been exacerbated by random in the same way. But, so, let's throw a wrench in this. Let's talk about distributed load balancing, because no one actually runs one load balancer. No one wants to have a giant single point of like failure in their system, right? So you run multiple. So how does that happen? How does that affect things? So if you're doing random, it's exactly the same. You just run random on all your load balancers, and it is identical to exactly what you were doing before. However, if you are doing join shortest queue, it is a goddamn nightmare. And so if anybody here has worked in distributed systems before, you know that like you can probably figure out why this is. That's because as soon as you have state that you're trying to keep in sync across multiple servers, it becomes very, very difficult. And servers start acting on outdated information and things start to go haywire, and that's exactly what we can see here. So this is what it looks like if you try to run join shortest queue across multiple load balancers at the same time. It starts to look much more like random, and in some cases actually even worse. And what's going on here, though? Let's pull it apart a little bit. So what you can see here is like that same view. This is the same information that was on that last slide, but broken out so that each of these is one application server. And so what you end up seeing here are waves, right? Oscillations. This is exactly that finger of death type thing that I was talking about earlier, because, you know, these servers are trying to share the state, and they all go, okay, we all see that this one doesn't have any traffic right now. Okay, we're all going to send our traffic there. And, okay, that one, no, let's switch back to the next one now. And so it's that kind of thing. Basically, they're trying to work on outdated information. So, must be some way that we can do this better, though. So, there's this paper called The Power of Two Choices in Randomized Load Balancing. It is from 1991, and yet, for some reason, no one is using it. That's not true. There are actually some systems that are using this now, but like, it was still a surprise to a lot of the people who I've talked to about this. So, the idea is this. Rather than just trying to use straight up join shortest queue, where you go, okay, this queue looks like it's the shortest, so I'm going to send my request to that one. The way the power of two choices works is that you choose two servers at random, choose two of those bins at random, essentially, and then you look at which one is shortest and which one's longest, and you choose a shorter one. So it's essentially reintroducing a small amount of randomness into the join shortest queue algorithm. Let's see what happens. So going back to, this is the code from earlier. This is where we're modeling like random load balancing with log normal. So let's try it with the like power of two choices algorithm. Again, we just modified the code slightly there to choose two at random. And then we choose the one that has the shortest length of queue. And it ends up looking like that. And so the paper predicts that it should be an exponential improvement in like the performance of the algorithm. It should be an exponential improvement in the variance of the essentially random versus the power of two choices. And that's exactly what we see. It ends up being really close to the join shortest Q algorithm most of the time, which is pretty impressive to me that just adding 2 lines of code to that actually made it this much better. And in fact, you can see, like, back to our simulations here, that ends up splitting the difference between the two. So, and again, and this is like one of the cooler things to me is that, like, so on the bottom we have join shortest Q, on the top we have random, in the middle we have the power of two choices. And especially as load increases, you see that, like, the power of two choices doesn't have that same effect that random has, where it actually makes things way, way, way worse as the load increases, which is pretty cool. So there are other approaches as well. When I was, like, doing this research, I looked into a whole bunch of different papers. This is another one of the Michael Mitzenmacher papers, How Useful is Old Information, where he basically takes a similar algorithm but makes it more complex, and it's like minor improvements over the power of two choices, but it's much more complex. This is a similar one. And then, so this one is actually just from, like, last year that someone published. It's like a brand new take on how to do load balancing, and it is so complex that I could not actually get it working, even in my simulations. So, you know, I think I'm probably going to stick with the power of two choices one. I don't know. There's some other crazy ideas that have come about recently as well. So this is a paper that was published by Microsoft Research in 2014, where it flips random on its head. So essentially, instead of having the load balancer go, I'm going to choose the app server at random, instead the app servers choose the load balancers at random and say when they are idle. So they join the idle queue on a random subset of the load balancers. And they actually show some, like, pretty impressive numbers for this, where the response time ends up looking better and better. So random is shown there in the purple, and then SQ2 is actually the power of two choices one, again. So that's the black line there. And then for the join idle queue one, they show that it's actually an improvement even beyond that, which is pretty impressive. So why does this matter? Well, all of it matters because the 99 to 99.9 percentiles are actually important, as it turns out. You're actually going to be hitting these on a regular basis, and users actually are going to suffer from them. And there's probably not much you can do about it on the front end, which is really unfortunate, but it is what it is in this case. So, like, this is a thing. Maybe if you're not an ops, maybe go yell at your ops people and tell them to fix this problem on their side. Try using a smarter algorithm for it. It's fine. One of my coworkers is upset because he used to be an ops. That's fine. But so the point, though, is this may help to explain performance issues as the site scales, as your particular website scales up. And that's really all I got for the evening. So I'm happy to answer whatever questions you have. Yes. I actually did see in some papers they were talking about this, and I hadn't tested it out. Essentially doing, like...
Can you repeat the
Right.
question? I apologize.
The question, or the statement, actually, was that one technique that this person has seen be successful in the past is essentially having the application servers remove themselves from the queue when they're overloaded, remove themselves from, like, the group when they're overloaded. And so I had actually seen some things about this and how it does improve. It's like relatively marginal improvements, but it's still an improvement, right? So cool, that's great, thank you. Right. So the question is, so when I was talking about the number of requests before you hit the 99th percentile of latency, this assumes that there's a uniform distribution. There's an equal probability of all of them hitting it. In some cases, yeah. In other cases, no, and that's, like, a totally reasonable critique that I totally didn't want to get into in the talk itself. And you were the first person to call it out, so thank you. So yeah, it depends, is honestly the answer. Yeah, okay. So the question is about, like, what about a kind of, like, learning load balancer that, like, tries to figure out the likelihood that some type of request is going to be heavier than another. And so this has come up repeatedly now. And I know at least of a couple different companies that have tried this. Google was one of them. And they ended up ripping it out because it was wrong too much of the time. And the problem is that, like, when you have a type of system that tries to load balance optimally, trying to guess, like, whether or not the request is going to be heavy or light, when it's wrong, it tends to be really wrong and end up making the system, like, worse. That was the answer that I got from them anyway.
I have a question actually. So you mentioned that in some websites actually make quite a lot of requests per page and before onload event fires. So how does this probabilistic distribution affect user experience in the end? Kind of why does this matter to end user? Let me rephrase it.
Right. So the question is like, why does this end up mattering to the end user? Which ultimately is just that like when you have that high number of requests, when you have this probability that like especially as load increases on your system, that you're going to start hitting those very high latencies, that like that long tail end of that this is going to not make it so that like your request that normally takes like 50 milliseconds is going to end up taking, as an outlier, like 300 milliseconds, right? And this kind of adds up over time, right? And so like that, especially as the number of individual requests per page goes up, it becomes more and more likely that a user is going to hit that on every load. And so the average latency for a page load ends up being higher.
So you're saying that it will not only affect the systems that are usually affected by the load, like database queries and things like that, but literally every request will be able to be affected or can potentially be affected by that.
Yeah, well, so that's the interesting thing about like that log normal distribution. One of the things that I've been reading in the past about it is how the essentially what creates that log normal distribution. It ends up being like a conglomeration of a lot of the different things that go into building things on the internet, right? So part of it is just like a necessary part. Part of it is like a necessary thing with asynchronous networks, where if a packet can be lost on a network, it means that you may have to retry that packet. And there's a certain probability of you losing a packet, which means that instead of going flat, it ends up starting to curve. And then once your request actually gets there, there's a probability that maybe you're going to hit garbage collection, or maybe you won't. Or maybe you're going to do a slow query on the database, or maybe you won't. And so ultimately, all of these things end up creating a steeper and steeper curve in that distribution. Yeah, so the question is there any way to make it not curve up at the end? Yeah, no, there really isn't, and like flat is actually impossible. Like in an asynchronous network, it is literally actually impossible. The question was, if doing join shortest queue in a distributed way is a nightmare, and power of two choices is basically just like using join shortest queue, but then doing like adding randomness to it, like how does that work? And the answer is that one of the things with join shortest queue and power of two choices is that when join shortest queue, sorry, let me back up. One of the things is that you need to share the information between all of the load balancers. So if you have 5 load balancers, they all have to talk to each other and think, okay, or and say, here's what I think the load on all the application servers are right now. And they just are continually telling each other what they think the loads are, right? And so with join shortest queue, when you try to go like, hey, I'm going to pick this one because it looks like it's shortest, it ends up acting on outdated information, right? The randomness that is part of power of two choices ends up essentially nullifying that. So the randomness that you reintroduce in that ends up going from like basically just flattening out the oscillations that end up happening. Yeah, they still have to communicate. It's just like the delays in communication have a like minimal effect. So I could almost barely not hear that. Was that you're asking about like how tight the latencies have to be when you're sharing that information? So essentially the answer to this is like, yeah, you like basically the tighter you have the latencies as you're sharing the information, the better it's going to be. And in fact, like when you have very, very small latencies, instead of doing the power of two choices, you can actually do the power of three choices, or the power of 4 choices. And like as the number of like choices that you make goes up, there becomes a higher probability that you are going to introduce oscillations, but the oscillations are less likely if you have lower latency. And so it ends up being a balancing act between those two things. So there is actually, and it's in the paper. I don't have it off the top of my head, but yeah, check out the paper. It like actually goes into not only the number, so it ends up being like a formula that goes between the number of buckets that you have, as well as the latencies involved in like sharing the information between. So the question was, what about not saying and trying actually just to send 2 requests to like multiple application servers? And so I tested this, and the answer is that is awesome, actually. So you get significantly improved performance if you do that, but it does require that you run like way more overhead, like more capacity than you would need otherwise. But if you can do that, then that is significantly better than any of the alternatives.
In your charts, you had like 50% load, 60% load, and so on, right? That affected that latency. why can't we just have more capacity than
Yeah.
we have? Why are we trying to always hit like 100% capacity, even with this method that you just described, the kind of like you're doubling capacity to achieve better performance? Why don't we just have more capacity to start with so we don't hit this?
What's that? Exactly. So like, yeah, no, absolutely. Like, if you can afford to do that, it is totally worthwhile to do. If you can't, because like doubling the capacity of say Fastly is quite a large investment for us, for instance.
It's just double.
It's just that is true. You run the risk of introducing like cache locality problems. It's true. And yeah, if you can afford to do that, then that's a totally worthwhile thing to do. If not, right, so you would have to write that yourself, unfortunately. That is, that paper was actually just introduced like a year and a half ago. So I don't know of anyone who's using it yet, but they're like their actual simulation data, and according to the paper, their actual like production uses of it at Microsoft Research have been really good. Yeah. Hopefully at some point they will like actually introduce an implementation of it.
One maybe last question,
right.
sorry. So we discussed how to improve load balancing to solve the problem of having fewer outliers, hitting fewer of those outliers. Is there anything to do in the application to avoid this problem to start with?
Sure. Right. So, all right, you have a mic. I don't need to repeat your question. So, the application is essentially what ends up controlling the steepness, the angle of that curve, right? And you are far more likely to start hitting really bad latencies, like if that curve is more, what do you call it, steeper, I guess in this case. On the other hand, if it stays flat all the way up to the 99.99th percentile, as I have actually seen in some of the use cases with some of the services on the CDN, then you have a far lower likelihood of hitting those. And so that is down to the application itself. So if you can avoid garbage collection, if you can avoid doing things that are heavyweight, if you can avoid things that like probabilistically will cause problems, then you can improve this. It's just that you can't fix it. It's still going to be